There is a language older than every human tongue ever spoken. It was being written long before the first city rose from the dust, long before the first hand pressed itself into wet clay and left a mark that said, "I was here." It existed before witnesses, before wonder, before we had a word for sky. It is written in pressure, in voltage, in the collision of warm air climbing against cold air falling. It is written in the spiral arms of systems so vast they can be seen from the edge of space, and in the single trembling droplet that clings to a window pane for just one breathless moment before the wind takes it. We call it weather, but that word is far too small. What you are about to witness is not simply a documentary about storms. It is an invitation into one of the most complex, most violent, most achingly beautiful systems that nature has ever assembled. From the physics of a single lightning bolt discharging 30,000 amperes in less than a millisecond, to the barometric pressure gradients that have redirected the courses of entire civilizations, the storm is not chaos. It has never been chaos. It is a symphony. Every element has its part. Every pressure system, its movement. Every cloud formation, its precise and irreplaceable role in the orchestration. And like all great symphonies, it begins in silence, in the gathering, in the waiting, in the almost unbearable tension of a sky that knows what it is about to become. Tonight we listen together. We will travel from the supercell thunderstorms of the American Great Plains to the perpetual hurricane locked in the atmosphere of Jupiter. We will descend into the science of ball lightning, the mythology of storm gods, the electromagnetic heartbeat of a planet that has been conducting this performance for 4.5 billion years without pause. And perhaps, somewhere in that vastness, you will find what many of our viewers have found before you, a strange, profound, and deeply human peace. If you are someone who finds calm in the sound of rain against the glass, if storms have always felt to you less like something to fear and more like something to feel, then you are exactly where you are meant to be. Subscribe to Starcom. Let this channel be the place you return to when the world is too loud and you need to remember that the universe has been making music long before any of us arrive to hear it. And before we begin, leave us a comment. Tell us where you are. Tell us what time it is where you are sitting right now. Because somewhere in the world, as you watch this, there is a storm occurring. There is lightning splitting a sky. There is a family listening to thunder roll across a valley. We want to know your corner of this vast, magnificent, storm-swept planet. Let the symphony begin. Before a storm is visible, before a single cloud has formed or a single raindrop has fallen, the storm already exists. It exists as potential, written invisibly into the arrangement of the atmosphere. Air masses of differing temperatures and moisture contents drift toward one another across continents and oceans, separated by boundaries meteorologists call fronts. Along these boundaries, the atmosphere is under tension. Warm, moist air from tropical regions moves poleward, rising when it meets the denser, cooler air of higher latitudes. This rising motion is the fundamental engine of storm development. As warm air ascends, it expands and cools, and the water vapor it carries begins to condense, releasing latent heat, a process that further accelerates the upward movement of the air column. What began as an invisible pressure differential becomes a towering, dynamic structure visible from hundreds of kilometers away. Every storm, no matter how catastrophic, begins here, in the quiet, invisible architecture of air masses obeying the elegant laws of thermodynamics, pressure, and the slow, rotational pull of a spinning world. Barometric pressure is among the most misunderstood concepts in everyday meteorology, and yet it governs nearly every atmospheric event we experience. At sea level, the weight of the entire column of atmosphere above a given point exerts a pressure of approximately 1,013.25 hectopascals, a figure so familiar to meteorologists it has become a kind of atmospheric middle C, the baseline note from which all weather deviates. When pressure falls, it signals that the air column above is becoming less dense, typically because warm air is rising and diverging at altitude. This creates a partial vacuum at the surface, and surrounding air rushes inward to fill it, producing the winds that characterize low-pressure systems. Hurricanes, typhoons, and nor'easters all owe their rotational fury to this basic principle. The lowest barometric pressure ever recorded at the Earth's surface was approximately 870 hectopascals, measured inside Typhoon Tip in 1979, a figure so extreme it represented a near-total collapse of the atmospheric column above the storm's center. Pressure, understood properly, is the breath of the sky. A cloud is not, as it might appear, a solid or even semi-solid object. It is a suspension, a vast community of liquid water droplets or ice crystals so small that the upward motion of the air within which they form is sufficient to hold them aloft against gravity. The process by which clouds form begins with a concept called the dew point, the temperature to which air must be cooled before the water vapor it contains begins to condense. When a parcel of air rises and cools to its dew point, condensation begins. But it cannot begin on nothing. Water vapor requires a surface upon which to condense, and in the open atmosphere, these surfaces are provided by microscopic particles called condensation nuclei, specks of sea salt, dust, smoke, pollen, and even bacteria. Without these tiny impurities, our skies would be dramatically clearer and our weather dramatically different. Each cloud droplet forms around a single condensation nucleus, and in a modest cumulus cloud, there are approximately 500 droplets per cubic centimeter, a number so vast it defies easy imagination, yet produces something as light and ephemeral as a summer cloud. Of all cloud formations documented in the International Cloud Atlas, none commands the atmosphere with the authority of the cumulonimbus. Known informally as the king of clouds, the cumulonimbus is the only cloud type capable of producing the full range of severe weather phenomena: lightning, thunder, torrential rain, hail, violent winds, and tornadoes. It develops from a modest cumulus cloud through a process of explosive convection driven by intense surface heating or powerful frontal lifting. Under the right thermodynamic conditions, a cumulonimbus can grow at rates exceeding 150 meters per minute, eventually piercing the tropopause, the boundary between the troposphere and stratosphere, at altitudes of up to 18 kilometers. At this ceiling, the cloud spreads horizontally into the characteristic anvil shape, named for its resemblance to a blacksmith's tool and visible from distances of hundreds of kilometers. Inside this structure, updrafts and downdrafts coexist at velocities that would tear an aircraft apart. It is architecture. It is violence. It is the most magnificent structure the atmosphere ever produces. The process by which a thunderstorm becomes electrically charged is, even now, one of the most actively researched areas in atmospheric science. The dominant theory involves the collision of ice particles within the cloud, specifically, the interaction between large, soft ice pellets called graupel and smaller ice crystals carried upward by the storm's updraft. When these particles collide, electrons are transferred between them. The smaller, lighter ice crystals, carrying a net negative charge, are lofted by the updraft toward the cloud's upper regions. The heavier graupel, carrying a net positive charge, sinks toward the base. Over time, this separation creates a powerful electric dipole within the cloud, a reservoir of electrical potential measured in hundreds of millions of volts. The electric field this generates extends downward to the Earth's surface, inducing a corresponding positive charge on the ground below. When the electric field strength exceeds the insulating capacity of the intervening air, approximately 3 million volts per meter under dry conditions, but significantly less in moist storm air, the insulation breaks down. The circuit closes, and lightning is born. What the human eye perceives as a single, instantaneous flash of lightning is, in reality, a rapid sequence of distinct physical processes occurring in fractions of a second. The sequence begins with the stepped leader, an invisible channel of ionized air that extends downward from the cloud base in discrete steps of approximately 50 meters, each step taking roughly 1 microsecond. As the stepped leader approaches the ground, the intensifying electric field below triggers upward moving streamers from tall objects, trees, buildings, people, reaching upward to complete the circuit. When leader and streamer connect, the channel is complete and the return stroke occurs, a massive surge of electrical current traveling upward through the established channel at roughly 1/3 the speed of light. This return stroke, carrying between 5 and 30,000 amperes of current, is the luminous flash we see. It is followed by a series of dart leaders and subsequent return strokes, typically 3 to 5, occurring within milliseconds, each reusing the original channel and producing the characteristic flickering quality of lightning. The entire event is complete in under 2 seconds. Thunder is the acoustic signature of lightning, the storm's voice made manifest through one of the most fundamental principles of physics. As the return stroke of a lightning bolt surges through its ionized channel, it heats the surrounding air almost instantaneously to temperatures approaching 30,000 Kelvin, approximately 5 times the temperature of the visible surface of the sun. This extreme, nearly instantaneous heating causes the air column to expand explosively at supersonic velocities, generating a cylindrical shock wave that propagates outward as sound. The characteristics of thunder, its initial sharp crack, followed by the long, rolling rumble, reflect the geometry of the lightning channel. The crack is produced by the segment of the bolt closest to the observer. The rumble is the integrated acoustic contribution of the channel's full length, arriving sequentially as sound from progressively more distant segments reaches the ear. Because sound travels at approximately 343 meters per second at standard conditions, each 3-second interval between the lightning flash and the first thunder corresponds to roughly 1 kilometer of distance. This simple calculation, the flash-to-bang method, has been used by storm observers for centuries to gauge proximity to danger. Among all the atmospheric phenomena cataloged by science, few are more genuinely enigmatic than ball lightning. Unlike conventional lightning, a well-understood electrostatic discharge, ball lightning appears as a luminous, roughly spherical object ranging from a few centimeters to over a meter in diameter. It has been reported in colors spanning the entire visible spectrum, described as moving slowly through the air, sometimes passing through glass windows, and occasionally disappearing silently or with a sharp report. Despite thousands of eyewitness accounts stretching back centuries and a small number of claimed instrumental detections, ball lightning has never been conclusively reproduced under controlled laboratory conditions, and no single theory has achieved scientific consensus. Proposed explanations range from microwave radiation trapped in a plasma bubble, to burning silicon vapor, to quantum mechanical effects on the ground following a conventional lightning strike. What makes ball lightning particularly difficult to study is its unpredictability and brief duration, typically between 1 second and several minutes. It occupies a strange territory in atmospheric science, witnessed, recorded, and undeniable in the historical literature, yet stubbornly resistant to formal scientific explanation. In 1805, a British naval officer named Francis Beaufort devised a standardized system for describing wind strength based on observable effects. A system so elegant in its design that it remains in use, in modified form, more than 2 centuries later. The Beaufort scale ranges from 0, defined as absolute calm with a glassy, mirror-like sea surface, to 12, defined as hurricane-force winds producing sea conditions described as exceptionally high waves, white foam covering the sea entirely, and visibility seriously impaired by driving spray. Each intermediate level carries equally evocative descriptions. Force 3 sees leaves in constant motion and small wavelets on open water. Force 6 sends large branches swaying and raises foam crests on the ocean surface. Force 9 sees slight structural damage to buildings and high waves with long overhanging crests. The scale is a remarkable fusion of empirical precision and poetic observation, a vocabulary for the wind invented by someone who understood that science and beauty are not opposites, but complements. Beaufort never saw his scale become famous. He died in 1857, before it was formally adopted internationally. When meteorologist Tetsuya Theodore Fujita introduced his tornado intensity scale in 1971, he created something that transcended a mere measurement tool. He created a taxonomy of catastrophe, a way of reading the damaged landscape left behind by violent tornadoes to infer the wind speeds that had produced it. The original Fujita scale ranged from F0, associated with light damage to chimneys and broken tree branches, to F5, described with remarkable bluntness as incredible damage. Strong frame houses leveled off foundations and swept away, automobile-sized missiles flying through the air in excess of 100 meters. The scale was revised in 2007 into the enhanced Fujita scale, which incorporated more sophisticated damage indicators and adjusted wind speed thresholds based on structural engineering research. The highest category, EF5, requires winds exceeding 89 meters per second, speeds at which even reinforced concrete structures suffer catastrophic failure. Only a handful of tornadoes in recorded history have been confirmed as EF5 events, yet each has left in its wake a corridor of absolute devastation that serves as a permanent, humbling record of the atmosphere's capacity for violence. Among the categories of thunderstorm documented by atmospheric science, the supercell stands apart, not merely in degree, but in kind. Unlike ordinary convective storms, which develop through relatively disorganized upward motion, the supercell is defined by the presence of a deep, persistent mesocyclone, a rotating updraft that can extend from near the ground to the upper troposphere and persist for hours. This rotation arises when horizontal tubes of spinning air, generated by wind shear in the lower atmosphere, are tilted into the vertical by the storm's powerful updraft. The result is a storm of extraordinary organization and longevity. Viewed from a distance, a supercell has a visual complexity unmatched by any other cloud formation, a striated, sculpted appearance, a lowering base called the wall cloud where the mesocyclone's rotation is most visible, a flanking line of congestus towers feeding into the main updraft, and often, a rotating appendage descending toward the ground that marks the precursor of a tornado. Supercells account for a disproportionate fraction of the most violent hailstorms, strongest tornadoes, and most extreme flash flooding events in the historical record. A tornado is, at its most fundamental, a manifestation of vorticity, the tendency of a fluid to rotate about an axis. In the atmosphere, vorticity exists at all scales, from the planetary rotation that drives the great cyclonic systems of the mid-latitudes down to the turbulent eddies that form in the wake of a moving vehicle. In a tornado, vorticity has been concentrated and intensified through a process called vortex stretching, the same physical principle that causes a spinning ice skater to accelerate as their arms are drawn inward. As the rotating column of air within a supercell's mesocyclone descends toward the surface, conservation of angular momentum causes its rotation to increase dramatically. The condensation funnel that typically makes a tornado visible is not the tornado itself. It is simply the region within the vortex where pressure has dropped sufficiently for condensation to occur. The actual circulation often extends well beyond the visible funnel, and debris lofted at the surface frequently reveals the true width of the damaging winds. The most violent tornadoes in history have produced tracks of destruction extending for hundreds of kilometers. No region on Earth produces more violent tornadoes per unit area than the broad, north-south corridor of the central United States, commonly known as Tornado Alley, a zone extending roughly from northern Texas through Oklahoma, Kansas, Nebraska, and into South Dakota. The meteorological preconditions for extreme tornado development align here with a frequency and regularity found nowhere else on the planet. The southern plains receive warm, moisture-laden air from the Gulf of Mexico with remarkable consistency during spring and early summer. This moisture streams northward and collides with cold, dry air descending from the Rocky Mountains and the Canadian interior, creating a sharp contrast in temperature, moisture, and density that provides the raw thermodynamic energy supercells require. Simultaneously, upper-level jet stream winds provide the vertical wind shear necessary to produce and sustain the rotating updrafts from which tornadoes descend. The combination of these factors creates a climatological firing range for supercell development. On particularly volatile days, known in storm chase culture as high-risk setups, dozens of supercells can erupt across the plains simultaneously, each capable of producing multiple violent tornadoes. These days have left marks on American history that have never faded. On the afternoon of March 18, 1925, a tornado descended from a supercell thunderstorm over the southeastern corner of Missouri and began a journey that would not end until it had crossed the entire state of Illinois and penetrated deep into Indiana, a continuous ground track of 352 kilometers, the longest ever confirmed for any tornado in recorded history. The tri-state tornado moved at forward speeds that by some estimates exceeded 100 kilometers per hour, offering the communities in its path almost no opportunity for warning or escape. In the towns of Murfreesboro, DeSoto, and Gorham in Illinois, destruction was total within the storm's path, which ranged from 1 to 2 kilometers in width. The final death toll, 695 confirmed fatalities, remains the greatest loss of life from any single tornado in United States history. Modern researchers who have re-examined the historical record using enhanced Fujita scale criteria believe the storm would have qualified as an EF5. The tri-state tornado endures not merely as a meteorological record, but as a monument to human vulnerability in the face of atmospheric violence, and a permanent argument for investment in early warning systems. In the annals of natural disaster, few events carry the weight of the Galveston hurricane of September 8, 1900, a catastrophe that remains, more than a century later, the deadliest natural disaster in United States history. Galveston, Texas, in 1900 was a prosperous, sophisticated city of approximately 40,000 people, built on a low-lying barrier island with a maximum elevation of no more than 2.7 meters above sea level. The hurricane made landfall as a Category 4 storm, driving a storm surge of approximately 4 to 5 meters that submerged the entire island. Between 6,000 and 12,000 people perished, estimates vary due to the catastrophic destruction of records, in a matter of hours. The storm obliterated more than 3,600 structures. The meteorologist Isaac Klein, who served as the local chief of the U.S. Weather Bureau, famously had written just 2 years earlier that a storm surge disaster at Galveston was essentially impossible. He spent the rest of his long life reassessing that certainty. In the aftermath, Galveston constructed a seawall 17 kilometers long and raised the grade of the entire city, a monumental engineering response to a meteorological humbling. The framework most commonly used by meteorologists and the public alike for communicating the intensity of Atlantic and Eastern Pacific hurricanes is the Saffir-Simpson Hurricane Wind Scale, a 5-category classification system based primarily on maximum sustained surface wind speeds. Developed in the early 1970s through collaboration between civil engineer Herbert Saffir and meteorologist Robert Simpson, the scale was created explicitly to communicate the expected level of damage associated with a given storm intensity. Category 1 storms, with winds between 119 and 153 kilometers per hour, produce minimal structural damage but may cause significant damage to unanchored mobile homes and vegetation. Category 5 storms, the scale's maximum, feature winds exceeding 252 kilometers per hour and are associated with catastrophic, near-total destruction of well-built frame homes, power outages lasting weeks to months, and uninhabitable conditions over large areas for an extended period. Critics of the scale have noted that it communicates wind intensity but does not directly indicate the threat from storm surge, which is historically responsible for the majority of hurricane fatalities. The scale has been revised and debated multiple times, reflecting the ongoing challenge of translating complex atmospheric science into actionable public communication. One of nature's most paradoxical and visually arresting features is the eye of a mature tropical cyclone, a region of descending air, light winds, and often clear skies that exists at the geometric center of one of the most violent atmospheric systems on Earth. The eye forms as the spiral bands of a developing hurricane organize around a central axis of intense low pressure. As air spirals inward toward the center, conservation of angular momentum causes its rotation to accelerate, eventually reaching speeds that prevent the air from continuing inward. Instead, the inflow rises explosively in the dense ring of thunderstorms surrounding the eye wall, and a compensating sinking motion develops within the eye itself. This descending air warms and dries as it compresses, suppressing cloud formation and producing the eerie calm that hurricane survivors often describe with a mixture of awe and dread. Eye walls in the most intense tropical cyclones can reach vertical extents of 18 kilometers, producing winds exceeding 300 kilometers per hour in a ring sometimes less than 20 kilometers wide around a center of relative tranquility. Standing in a hurricane's eye is among the most disorienting experiences the atmosphere can offer. Among the most persistent and consequential challenges in tropical meteorology is the problem of rapid intensification, the process by which a tropical cyclone's maximum sustained winds increase by 35 kilometers per hour or more within a 24-hour period. Rapid intensification events are responsible for many of the world's most catastrophic hurricane disasters because they can transform a manageable storm into a potentially unsurvivable one in a time frame far shorter than evacuation procedures typically require. The physical processes driving rapid intensification involve a complex interaction between the storm and its environment, warm sea surface temperatures extending to depth, low vertical wind shear, dry air intrusion patterns, and internal structural changes within the eyewall itself. In 2023, Hurricane Otis underwent one of the most extreme rapid intensification events ever recorded over the eastern Pacific, intensifying from a Category 1 to a Category 5 storm in approximately 12 hours before making landfall near Acapulco, Mexico, with devastating consequences. Despite significant advances in computational modeling and observational technology, the prediction of rapid intensification events remains one of the most difficult problems in operational weather forecasting. High above the Arctic, circling the pole at altitudes between 15 and 50 kilometers, there exists a vast cyclonic circulation of frigid stratospheric air known as the polar vortex. It is a permanent feature of the winter atmosphere, a wall of strong westerly winds that normally keeps the coldest Arctic air confined to high latitudes. The polar vortex is maintained by the steep temperature gradient between the pole and the mid-latitudes, and its integrity is enforced by a feature of atmospheric dynamics called the stratospheric jet stream. When the polar vortex is strong and undisturbed, it acts as an effective barrier, and winters in the mid-latitudes tend toward relatively mild and stable conditions. When it weakens, a process called sudden stratospheric warming, which can raise stratospheric temperatures over the pole by 50 degrees Celsius or more within a matter of days, the vortex can become unstable, distorted, and ultimately split, allowing lobes of extremely cold Arctic air to plunge southward into the mid-latitudes of North America, Europe, and Asia. These displacement events produce the anomalously cold winter outbreaks that generate headlines, freeze water mains, and strand travelers. The polar vortex escaped from its confinement, stretching thousands of kilometers across the mid-latitude atmosphere, often no wider than 500 kilometers but carrying moisture fluxes comparable to multiple times the average discharge of the Amazon River. Atmospheric rivers are among the most consequential meteorological phenomena for water resources worldwide, and among the least familiar to the general public. An atmospheric river is essentially a narrow corridor of concentrated water vapor transport in the lower atmosphere, typically found at altitudes between 1 and 3 kilometers, that connects tropical and subtropical moisture sources to the mid-latitudes. When an atmospheric river makes landfall, particularly when it is directed by the jet stream into mountain ranges like the Sierra Nevada, the Cascades, or the Atlas Mountains, the forced lifting of moist air produces extraordinarily intense precipitation events. The western United States depends on atmospheric rivers for a substantial fraction of its annual precipitation and snowpack, which in turn provides much of the region's fresh water supply. But the same systems that replenish reservoirs can trigger catastrophic flooding and debris flows when they are particularly intense or persistent. The informal term, Pineapple Express, is used colloquially to describe atmospheric rivers originating near Hawaii and directed toward the Pacific coast of North America. While tornadoes receive the majority of public attention in discussions of severe convective weather, the derecho, a widespread, long-lived system of destructive straight-line winds associated with a fast-moving band of severe thunderstorms, is arguably more broadly impactful in terms of total economic damage and geographic extent. A derecho is defined technically as a line of wind damage extending at least 400 kilometers, with gusts of at least 93 kilometers per hour and multiple wind damage reports across the full swath. These events are produced by bow echoes, crescent-shaped radar signatures that develop when powerful rear-flank downdrafts within a squall line accelerate outward, creating a bookend structure around a region of intense surface winds. The winds in a major derecho are not the rotating, vertically oriented vorticity of a tornado, but a horizontal, outward exploding blast front. On August 10, 2020, a derecho swept across Iowa and into Illinois and Indiana, producing wind gusts of up to 140 kilometers per hour and causing approximately $7.5 billion in crop and infrastructure damage, one of the costliest weather events in Iowa's recorded history. It passed largely without national headlines. Among winter weather phenomena, the ice storm occupies a unique position. It is simultaneously one of the most visually spectacular and one of the most economically destructive events the atmosphere produces. Ice storms occur when precipitation falls as liquid rain through a layer of above-freezing air but subsequently passes through a shallow layer of below-freezing air near the surface, arriving at the ground as supercooled liquid water that freezes on contact with any exposed surface. The resulting glaze ice coating is indiscriminate. It coats every branch, every wire, every blade of grass, every road surface with an equal crystalline weight. The beauty produced, a landscape transformed into a chandelier, every surface catching and refracting light, is genuine and remarkable. But the weight is also genuine. A single ice storm can deposit several centimeters of glaze on power lines, adding weight sufficient to collapse transmission towers that were engineered to survive decades of normal loading. Trees snap under the weight, blocking roads and striking structures. The January 1998 North American ice storm, which affected large portions of Quebec, Ontario, New York, and New England, left more than 4 million people without power, some for over a month, in temperatures well below freezing. It remains one of Canada's costliest natural disasters. Hailstones are the atmosphere's artillery, ice projectiles manufactured within the intense updrafts of severe thunderstorms and hurled earthward with velocities that can exceed 170 kilometers per hour. The formation process begins when a supercooled water droplet is lofted into the freezing upper regions of a cumulonimbus updraft, where it freezes into a tiny ice embryo. This embryo then circulates within the storm, carried upward by updrafts into regions of supercooled liquid water, where successive layers of ice accumulate, then descending partially before being relofted for additional coating. The duration of this cycling process determines the final size of the hailstone. Cutting a hailstone in cross-section reveals concentric rings of alternating clear and opaque ice. A stratigraphic record of the stone's history within the storm, not unlike the rings of a tree. The largest hailstone ever officially documented in the United States fell in Vivian, South Dakota, on July 23, 2010, a disc-shaped stone measuring 20 centimeters in diameter and weighing nearly 900 grams. An object of that mass falling at terminal velocity delivers impact energy sufficient to penetrate roof materials, shatter windshields, and cause fatal injury to unprotected individuals. In the desert regions of North Africa, the Arabian Peninsula, the American Southwest, and the Indian subcontinent, the approach of certain severe thunderstorms is announced not by rain but by a wall of suspended dust and sand that can reach altitudes of 1,500 meters or more and advance at speeds exceeding 60 kilometers per hour. This phenomenon, the haboob, is generated by the powerful outflow of cold, dense air from a decaying thunderstorm's downdraft. As this air spreads outward from the storm's base, it acts as a horizontal piston, scouring the desert surface and lifting vast quantities of particulate matter into suspension. The leading edge of a haboob, viewed from a distance, presents one of the most dramatic spectacles in atmospheric science. A rolling, churning wall of reddish-brown or ochre-colored air, its base obscuring the horizon entirely and its upper boundary folding forward in turbulent crests. Visibility within a haboob can drop to 0 in seconds. Haboobs in the Khartoum region of Sudan, where some of the most historically documented events have occurred, can completely bury structures in sand within minutes. In Phoenix, Arizona, summer haboobs generated by monsoon thunderstorm outflows have become increasingly well-documented and photographically striking events that draw significant public attention. Where the atmosphere meets the ocean surface, a phenomenon develops that shares the visual drama of a tornado but often differs in its dynamics and origin, the waterspout. Two distinct categories of waterspout are recognized by meteorologists. Tornadic waterspouts are genuine tornadoes that form over water, typically produced by supercell thunderstorms or other severe convective systems, and they carry all the destructive potential of their land-based counterparts. Fairweather waterspouts, by contrast, form in relatively benign atmospheric conditions, often under developing cumulus clouds over warm tropical or subtropical waters, through a bottom-up process quite different from the top-down descent of a tornadic vortex. These fairweather systems are generally less intense, shorter-lived, and considerably less dangerous than tornadic waterspouts, though they remain capable of causing significant damage to small watercraft. The Florida Keys are among the most active waterspout locations on Earth, with hundreds of fairweather events documented annually. Throughout maritime history, waterspouts have generated legends far out of proportion to their actual threat. Accounts of ships swallowed whole by spinning sea columns populate the historical record, though the actual risk to large vessels was routinely exaggerated by sailors for whom the sea's inexplicable behavior required equally dramatic explanation. The word monsoon, derived from the Arabic mausim, meaning season, describes one of the most important and largest-scale meteorological phenomena on Earth, the seasonal reversal of wind direction and associated precipitation regimes that affects large portions of South and Southeast Asia, West Africa, the Australian interior, and the American Southwest. The South Asian or Indian monsoon is the most celebrated and consequential of these systems, providing approximately 80% of India's annual rainfall within a 4 to 5 month period between June and September, and directly supporting the agriculture and water security of more than 1 billion people. The monsoon's fundamental driver is the differential heating between land and ocean on seasonal timescales. As the Eurasian continent heats intensely during the northern hemisphere summer, a vast thermal low-pressure system develops over the subcontinent, drawing moisture-laden air onshore from the Indian Ocean. The onset of the monsoon, marked by the arrival of sustained rainfall and the dramatic lowering of temperatures, is experienced not merely as a meteorological transition but as a cultural and spiritual event across the subcontinent, celebrated in music, poetry, and religious observance across millennia of human civilization. At altitudes of roughly 9 to 16 kilometers above the Earth's surface, in the upper troposphere and lower stratosphere, there exist narrow, fast-moving currents of air called jet streams, atmospheric rivers of wind that can reach speeds of 450 kilometers per hour and span the globe in an undulating path that shifts seasonally and reacts to the temperature contrasts below. The jet streams form at the boundaries between air masses of significantly different temperatures. The polar jet stream at the boundary between polar and mid-latitude air masses, the subtropical jet at the boundary between mid-latitude and tropical air. Their existence was not confirmed until aircraft began flying at high altitude during World War II, when American B-29 bombers attempting to bomb Japan from the east encountered winds that either halted their progress entirely or accelerated them to ground speeds that made precision bombing impossible. The jet stream is not merely an interesting meteorological feature, it is the principal mechanism by which mid-latitude weather systems move. It steers storms, guides atmospheric rivers, determines the track of hurricanes, and plays a central role in the long-range predictability of weather. Recent research suggests that Arctic amplification, the faster warming of the Arctic relative to the mid-latitudes, may be causing the jet stream to slow and undulate more dramatically, with significant consequences for extreme weather persistence. A cloud that forms at ground level is, by definition, fog, and yet the word captures something that cloud does not. The intimate, obliterating quality of an atmosphere become opaque, of a world reduced to what can be seen within a radius of a few meters. Fog forms through several distinct mechanisms. Radiation fog develops on calm, clear nights when the ground radiates heat rapidly and the lowest layer of air cools below its dew point, a process most common in valleys where cold air pools and drainage promotes accumulation. Advection fog forms when warm, moist air moves over a cooler surface, as when tropical maritime air flows over the cold California current off the Pacific coast, producing the persistent fog that envelopes San Francisco with a frequency that has shaped both its architecture and its cultural identity. Sea fog and Arctic sea smoke form through analogous processes over ocean surfaces. Upslope fog forms when moist air is forced up a mountain slope and cools adiabatically to saturation. The Grand Banks of Newfoundland, where warm Gulf Stream water meets the cold Labrador Current, is among the foggiest marine locations on Earth, and the site of countless maritime disasters across the centuries. where fog transformed familiar sea lanes into fatal labyrinths. On the sun-baked plains of deserts, dry lake beds, and freshly harvested fields, a seemingly self-organizing phenomenon develops with remarkable regularity on hot, sunny days. The dust devil, a rotating column of rising air made visible by the dust and debris it entrains. Unlike tornadoes, dust devils form from the bottom up, driven by convective instability at the surface rather than by rotating mesocyclones aloft. On intensely heated surfaces, localized pockets of air warm faster than their surroundings and begin to rise. If conditions are right, a hot surface, relatively calm background winds, sufficient surface instability, this rising air begins to rotate due to minor horizontal vorticity in the ambient environment, and a dust devil forms. They are generally benign phenomena, rarely producing winds sufficient to cause significant structural damage, though large ones have been documented with wind speeds exceeding 100 kilometers per hour. What is perhaps most remarkable about dust devils is that they are not unique to Earth. The Mars exploration rovers Spirit and Opportunity and the InSight lander have all documented Martian dust devils passing overhead, some reaching heights of 8 kilometers, dwarfing anything seen on Earth, driven by the extreme surface heating of a thin atmosphere over a rust-colored desert. Approximately every 2 to 7 years, a large-scale disruption of the coupled ocean-atmosphere system of the tropical Pacific produces a cascade of meteorological consequences felt in every corner of the world. This disruption, El Niño, named by Peruvian fishermen for the Christ child whose birth it appeared to herald with its typical December arrival, represents a fundamental reorganization of the heat distribution and circulation patterns of the planet's largest ocean. Under normal conditions, strong trade winds drive warm surface water westward across the Pacific, accumulating it in a vast warm pool near Australia and Indonesia while drawing cold, nutrient-rich water upward along the South American coast. During El Niño, these trade winds weaken or reverse. The warm water spreads back eastward across the Pacific, raising sea surface temperatures across the central and eastern tropical Pacific by several degrees Celsius. This temperature anomaly alters the position of the jet streams, the probability of drought or flooding in dozens of regions, the frequency and intensity of Atlantic hurricanes, and the incidence of wildfires across Australia and Southeast Asia. The 1997 to 1998 El Niño event, among the strongest ever recorded, was associated with weather disasters on 6 continents and estimated economic damages exceeding $35 billion. Following an El Niño event, sometimes separated from it by only months, a near-opposite phase of the same coupled ocean-atmosphere oscillation frequently develops, La Niña, characterized by an anomalous cooling of tropical Pacific sea surface temperatures as the trade winds strengthen and warm water is pushed unusually far westward. Where El Niño suppresses Atlantic hurricane activity through increased wind shear, La Niña tends to reduce shear and enhance conditions favorable for tropical cyclone development. Where El Niño brings drought to Australia and flooding to coastal South America, La Niña reverses these patterns. The El Niño Southern Oscillation Cycle, encompassing both extremes and the neutral states between them, represents the most powerful source of year-to-year climate variability on Earth, and its accurate prediction has been one of the signal achievements of modern meteorological science. Extended-range seasonal forecasts issued months in advance can now predict El Niño and La Niña events with substantial skill, enabling governments, water managers, agricultural planners, and disaster preparedness officials to make decisions based on probabilistic information about coming seasons. The cycle is ancient, but our ability to anticipate it is new, a testament to what satellite technology, ocean buoy networks, and computational fluid dynamics have made possible in a remarkably short time. The nitrogen that forms roughly 78% of Earth's atmosphere is, in its molecular form, almost chemically inert, held together by one of the strongest triple bonds in chemistry, resistant to the reactions that would allow it to enter biological systems. Yet life requires nitrogen in a reactive form, as ammonia, as nitrates, as the building blocks of amino acids and nucleic acids. The conversion of atmospheric nitrogen into biologically available compounds, nitrogen fixation, is accomplished primarily by specialized microorganisms, but a significant secondary pathway exists in a most unexpected place, within the plasma channel of a lightning bolt. The extraordinary temperatures generated by the return stroke, approaching 30,000 Kelvin, are sufficient to break the nitrogen triple bond, allowing nitrogen atoms to combine with oxygen to form nitrogen oxides. These compounds dissolve in precipitation and are deposited on the soil surface as nitrate, a form of nitrogen directly available to plants. Global lightning discharges, estimated at approximately 40 to 50 per second, fix between 5 and 8 teragrams of nitrogen per year through this mechanism. It is a small but ancient contribution to the global nitrogen cycle, the storm nourishing the soil it strikes, the violence becoming, at the molecular scale, a gift. By the mid-18th century, the theoretical framework for understanding electricity as a natural phenomenon was solidifying rapidly, driven in no small part by the experiments of one of the most restlessly curious minds in American intellectual history, Benjamin Franklin. Through his famous kite and key experiments, which were considerably more sophisticated and considerably more dangerous than the popular imagination suggests, Franklin demonstrated the electrical nature of lightning and reasoned that if a conductor were placed in electrical contact between a storm cloud and the ground, lightning would preferentially follow it rather than strike structures. His invention of the pointed lightning rod, published in his almanac in 1753, was among the most consequential practical applications of scientific reasoning in history. Prior to lightning protection, European church towers, the tallest structures in most communities, were struck with devastating regularity, killing bell ringers who continued to ring during storms in the belief that the sound repelled lightning. Franklin's invention was adopted with remarkable speed across both America and Europe, though not without theological controversy. Some clergymen argued that diverting lightning constituted interference with divine will. The debate was settled, essentially, by continued strikes on unprotected churches and the conspicuous safety of protected structures. The emergence of professional and scientific storm chasing as a recognized discipline of atmospheric science in the latter half of the 20th century represents one of the more unusual marriages of technology, courage, and intellectual curiosity in the history of meteorology. The practice of deliberately intercepting severe thunderstorms and tornadoes to make close-range observations developed from the recognition that the instruments available at fixed weather stations were simply insufficient to capture the fine-scale structure and physics of short-lived, highly localized convective phenomena. Early storm chasers, including the legendary Tetsuya Fujita, who used aerial photography of tornado damage paths to develop his intensity scale, worked with tools that seem primitive by modern standards. The 1996 Hollywood film Twister introduced the broader public to storm-chasing culture, though it took considerable liberties with the science. Modern research vehicles like the Doppler-on-Wheels mobile radar systems can map the wind fields within a tornado with resolution that was unimaginable 40 years ago. Teams like those associated with the Vortex and Vortex 2 research programs have placed instrumented pods in the paths of tornadoes to sample the near-surface environment within the vortex itself, a scientific endeavor that is, without question, one of the more extraordinary examples of human beings putting themselves in harm's way in pursuit of knowledge. When the Voyager spacecraft made their flybys of Jupiter in 1979, they returned images of a planet whose visible surface was one continuous meteorological spectacle, a world of banded cloud systems, zonal jet streams, and convective plumes arranged in a complexity that made Earth's weather systems look modest by comparison. At the center of this spectacle was a feature known to observers since at least the 17th century, the Great Red Spot, a high-pressure storm system of anticyclonic rotation sitting in Jupiter's southern hemisphere that has persisted as a coherent structure for at minimum 350 years, and possibly much longer. At its largest historical extent, the Great Red Spot was wide enough to contain 3 Earths side by side. In recent decades, observations by the Hubble Space Telescope and the Juno spacecraft have documented a disconcerting shrinkage. The storm has been contracting in its east-west dimension, and its characteristic reddish coloration, still not definitively attributed to any specific chemical compound, has fluctuated. Whether the Great Red Spot is dying, restructuring, or merely undergoing a temporary contraction remains an open question in planetary science. Jupiter's storms remind us that the storm is not merely a feature of Earth, it is a feature of atmospheres. If Jupiter's Great Red Spot represents a storm that challenges our sense of scale, Saturn's North Polar Hexagon challenges our sense of what atmospheric dynamics can produce. First observed by Voyager 1 in 1980 and subsequently confirmed by the Cassini spacecraft in extraordinary detail, the hexagon is a persistent, six-sided jet stream pattern that encircles Saturn's North Pole at approximately 77 degrees north latitude. Each side of the hexagon measures approximately 13,800 kilometers, a length greater than the diameter of the Earth. At the center of the hexagon sits a powerful cyclone with a well-defined eye wall structure reminiscent of a terrestrial hurricane, but on a scale roughly 50 times larger. The hexagon's straight sides and sharp corners represent a feat of fluid dynamics that initially defied simple explanation. The current scientific consensus holds that the geometry is produced by a standing Rossby wave, a type of atmospheric wave generated by the interaction of the polar jet stream with slower-moving flow at lower latitudes. Laboratory experiments using rotating tanks of fluid have reproduced hexagonal and other polygonal flow patterns under the right conditions, confirming that the hexagon is a genuine atmospheric fluid dynamics phenomenon rather than a surface feature. If Earth's atmosphere seems complex and occasionally violent, Venus offers a vision of atmospheric physics taken to an extreme that borders on the surreal. The surface atmospheric pressure on Venus is approximately 92 times that of Earth at sea level, comparable to the pressure experienced at a depth of 900 meters in Earth's oceans. The temperature at the surface averages around 465 degrees Celsius, maintained by a runaway greenhouse effect driven primarily by a near-pure carbon dioxide atmosphere. Above this suffocating surface environment, the atmosphere of Venus is in constant, global motion, at an altitude of approximately 60 kilometers, where temperatures and pressures are more Earth-like. Sulfuric acid clouds circulate in jet streams that carry them around the planet in approximately 4 Earth days, a phenomenon called superrotation, in which the atmosphere moves roughly 60 times faster than the solid planet below. Within these cloud layers, lightning has been detected by multiple spacecraft, though its frequency and origin remain debated. The storms of Venus, if they can be called storms in any familiar sense, are less events than they are conditions, the perpetual, planet-wide, chemical violence of an atmosphere that followed a different evolutionary path. Neptune is the most distant planet in the solar system, receiving solar radiation approximately 900 times weaker than Earth, and yet it possesses the most violent atmospheric dynamics of any body we have observed in detail. Wind speeds in Neptune's atmosphere have been measured at over 2,000 kilometers per hour, making them the fastest planetary winds in the solar system, a fact that remains deeply puzzling to planetary scientists. Where does the energy come from to drive winds of such extraordinary velocity on a world so remote from the Sun? The answer appears to lie within Neptune itself. The planet radiates approximately 2.6 times more energy than it receives from the Sun, suggesting a powerful internal heat source, possibly residual heat from the planet's formation, that drives vigorous convection throughout the deep atmosphere. The Voyager 2 flyby in 1989 documented a massive anticyclonic storm system called the Great Dark Spot, analogous in some respects to Jupiter's Great Red Spot, with white cirrus-like clouds of methane ice streaming along its boundaries. When Hubble observations in 1994 searched for the Great Dark Spot, it had disappeared, a reminder that even the most imposing atmospheric systems are ultimately transient. Saturn's moon Titan occupies a unique position in the solar system. It is the only moon with a dense atmosphere and the only world besides Earth where stable liquid is known to exist on the surface. But on Titan, the role that water plays in Earth's weather cycle is fulfilled by methane. The atmospheric temperature of approximately minus 179 degrees Celsius means that methane exists on Titan in all 3 phases simultaneously, as a gas in the atmosphere, as clouds at altitude, and as liquid in lakes and seas that cover parts of the polar regions. Convective methane storms, analogous in their dynamics to Earth's convective rain systems, have been observed both by the Cassini spacecraft and inferred from surface features. These storms are thought to occur episodically, perhaps seasonally, and when they do, they may deposit large quantities of liquid methane on Titan's surface, driving flash floods across landscapes of water ice and organic sediment. The Huygens probe, which descended through Titan's atmosphere in January 2005, returned images of drainage channels and what appeared to be a coastline, features carved not by water, but by methane precipitation falling from methane clouds in a methane rain cycle under a nitrogen sky. When a flowing fluid encounters a blunt obstacle, the orderly flow around the obstacle can break down into a regular, alternating pattern of vortices shed alternately from either side of the object, a phenomenon known as the Kármán vortex street, named for the Hungarian-American aerodynamicist Theodor von Kármán, who provided its theoretical treatment in 1911. In the atmosphere, Kármán vortex streets are produced when stable air flows around isolated islands or mountain peaks that protrude above the main cloud layer. The vortices shed into the wake of the obstacle are visible from satellite imagery as extraordinarily regular, alternating spiral patterns extending downwind for hundreds of kilometers, among the most aesthetically striking patterns visible from space. The clouds in each vortex rotate in opposite directions, producing a chain of alternating cyclones and anticyclones with a regularity that appears almost computational. Islands that frequently generate these patterns include the Canary Islands, Guadalupe Island off Baja California, and Jan Mayen in the Arctic Ocean. Beyond their visual appeal, atmospheric Kármán vortex streets have practical implications. The oscillating lift forces generated by the same mechanism are responsible for the resonant oscillation that can cause engineering structures like bridge decks and power lines to vibrate, and in the extreme case of the Tacoma Narrows Bridge, to fail catastrophically. Of all the hazards associated with landfalling tropical cyclones, storm surge, the abnormal rise of sea level above the normal tide level caused by the wind and low pressure of the approaching storm, is historically responsible for the greatest loss of life. It is also, paradoxically, the hazard least understood by the general public. A storm surge is not a tsunami-style wave. It is an elevated dome of water, sometimes several meters above normal sea level, that rides beneath and ahead of the storm and moves ashore as the storm makes landfall. The water level rise is driven by two mechanisms: wind stress on the ocean surface, which piles water toward the coast, and the inverse barometer effect, where the low atmospheric pressure at the storm's center allows the sea surface to bulge upward. The geometry of the coastline profoundly influences surge height. Shallow, funnel-shaped bays can dramatically amplify the surge above open coast values. Cyclone Bola, which struck the coast of what is now Bangladesh in November 1970, generated a storm surge estimated at up to 10 meters that inundated the low-lying Ganges-Brahmaputra Delta and killed between 300,000 and 500,000 people, a figure that stands as a permanent, sobering benchmark for the storm's capacity for mass casualty. Along the eastern slopes of the Rocky Mountains, particularly in Alberta, Canada, and the northern plains states of the United States, one of the most dramatic and meteorologically spectacular temperature change events in the world occurs with periodic regularity. The Chinook, a warm, dry wind that descends from the mountains and can raise temperatures by 20 to 30 degrees Celsius within minutes, transforming a snow-covered landscape into bare ground within hours. The Chinook is a fen wind, a category of warm, dry downslope wind found wherever stable air is lifted over a mountain barrier, loses moisture on the windward side through precipitation, and descends on the leeward side, warming at the dry adiabatic rate throughout its descent. The net result is air considerably warmer and drier on the leeward side than on the windward side, even at the same altitude. The indigenous peoples of the Great Plains named this wind the Snow Eater, a description both vivid and accurate. The most extreme recorded temperature change associated with a Chinook occurred in Spearfish, South Dakota, on January 22, 1943. The temperature rose from -20 degrees Celsius to +7 degrees Celsius in 2 minutes, a change of 27 degrees in 120 seconds that shattered thermometers across the town. From the Sahara Desert, Periodically throughout the year but most consistently in spring and autumn, a meteorological system develops that carries the heat and dust of the world's largest hot desert northward across the Mediterranean Sea, depositing reddish Saharan sand on car windshields as far north as England and raising temperatures across southern Europe by 10 to 15 degrees Celsius above seasonal norms. This wind system is known across different portions of its range by different names: the Sirocco in North Africa and Italy, the Khamsin in Egypt, the Lavesh in Spain, but its fundamental character is consistent: a hot, dry, dust-laden southerly or southeasterly wind ahead of a deepening low-pressure system tracking eastward across the Mediterranean. The Sirocco's arrival has been documented throughout Mediterranean history as a source not merely of discomfort but of psychological disturbance. Historical accounts and modern medical literature both describe elevated rates of headache, irritability, sleep disturbance, and anxiety among populations exposed to prolonged Sirocco conditions, effects attributed variously to heat, low humidity, increased concentrations of positive ions, and the fine particulate load of Saharan dust in the respired air. The wind that shaped the Sahara still shapes, in some small measure, the people who live in its shadow. The history of weather forecasting is, in many ways, the history of the confrontation between scientific ambition and atmospheric complexity, a story of incremental, hard-won progress achieved over generations of meteorologists who understood that the atmosphere's behavior was deterministic in principle but chaotic in practice. The first operational weather forecasting service was established in Britain in 1854 under the direction of Vice Admiral Robert Fitzroy, the same Fitzroy who had captained HMS Beagle during Charles Darwin's voyage, following a catastrophic storm that sank the Royal Charter off the coast of Wales and killed approximately 450 people. Fitzroy introduced the storm warning system, the precursor of modern weather forecasting, using the newly available electric telegraph to transmit meteorological observations across Britain rapidly enough to provide meaningful warning time. His methods were sometimes criticized by scientists who felt his forecasts exceeded the available evidence, and Fitzroy himself, a deeply religious man who struggled with the intersection of his scientific work and his faith, eventually took his own life in 1865. Modern numerical weather prediction, which translates the equations of fluid dynamics and thermodynamics into computational form and integrates them forward in time, is a direct descendant of the vision that Fitzroy's observatory first articulated. In 1961, a meteorologist at the Massachusetts Institute of Technology named Edward Lorenz was running a simple atmospheric simulation model on an early computer when he made a discovery that would eventually reshape multiple branches of science. Returning to a previous simulation, Lorenz restarted it from a printout that showed the initial conditions rounded to 3 decimal places rather than the 6 decimal places stored in the computer's memory. He expected the results to converge with the original simulation rapidly. Instead, the tiny rounding error in the initial conditions amplified exponentially, and within a simulated period of a few months, the two simulations diverged so completely that they bore no resemblance to each other. This was not a computational error. It was the atmosphere, even in simplified model form, revealing its fundamental sensitivity to initial conditions. Lorenz published his findings and eventually coined a phrase that has escaped the technical literature entirely and entered the general vocabulary: the butterfly effect. The notion that the flap of a butterfly's wings in Brazil might, through the chaotic amplification of small perturbations, set off a tornado in Texas. It was poetic, memorable, and scientifically imprecise, but it captured something genuinely true about the limits of long-range atmospheric prediction that no amount of computational power can ultimately overcome. Long before Francis Beaufort codified his wind scale, human societies had been developing their own systems for measuring, describing, and predicting the behavior of storms, motivated not by scientific curiosity but by the urgent practical necessity of maritime navigation and agricultural survival. In ancient China, meteorological observations were made systematically from at least the 3rd century BCE, with court records documenting wind, rain, and extreme weather events in consistent, standardized terminology. The Chinese invention of the wind vane, used to determine wind direction, predates European equivalents by centuries. In the Indian Ocean basin, Arab and South Asian navigators developed sophisticated empirical knowledge of monsoon seasonality that allowed them to make transoceanic voyages with remarkable regularity and reliability centuries before the European age of exploration. The Polynesian peoples of the Pacific developed navigational techniques based on wind, swell, and star patterns that allowed them to find and settle islands across the largest ocean on Earth without instruments of any kind. These traditions represent a different kind of meteorological science, observational, empirical, and deeply practical, that accumulated over centuries of human experience with the consequences of being wrong about the weather. Beyond its visible and acoustic manifestations, a lightning discharge produces an electromagnetic signature of remarkable complexity and reach, a transient electromagnetic pulse that propagates both within the Earth ionosphere waveguide and outward into space, and that has proven invaluable as both a scientific tool and a communications phenomenon. The radio waves generated by lightning, called spherics, short for atmospherics, were among the first natural radio signals ever detected, observed in the earliest days of radio technology as crackling interference on receivers tuned to medium and low frequencies. They propagate globally within the waveguide formed between the Earth's surface and the ionosphere, allowing a single lightning stroke in the Amazon basin to be detected by receivers in Europe within a fraction of a second. Networks of spheric detectors around the world are now used to create real-time, global lightning location maps with sub-kilometer accuracy, an extraordinary inversion of what was once considered mere interference. The electromagnetic pulse of a nuclear detonation operates on somewhat analogous principles but at vastly greater energies, and early nuclear strategists' concern about EMP effects was partly informed by study of the electromagnetic environment that global lightning activity already creates, the planet's own, self-generated, perpetual electromagnetic weather. At altitudes between approximately 60 and 1,000 kilometers above the Earth's surface lies the ionosphere, a region of the upper atmosphere where ultraviolet and X-ray radiation from the sun ionizes gas molecules, creating a plasma layer that reflects certain radio frequencies and plays a central role in long-distance radio communication. The ionosphere also forms the upper boundary of a natural electromagnetic cavity, the space between the Earth's surface and the ionosphere, that supports resonant electromagnetic standing waves. These resonances, first predicted theoretically by the physicist Winfried Otto Schumann in 1952 and subsequently confirmed by measurement, occur at specific frequencies, of which the fundamental is approximately 7.83 Hz. The energy that drives the Schumann resonances comes almost entirely from lightning. The approximately 40 to 50 lightning strikes occurring globally every second collectively act as a distributed electromagnetic source maintaining the cavity in a state of perpetual resonance. The Schumann resonances have been proposed as a global thermometer of sorts, since their frequencies and intensities are sensitive to the global distribution and total activity of lightning, which is in turn sensitive to global surface temperatures. They have also attracted interest and considerable pseudoscientific embellishment in discussions of human brainwave entrainment and the putative synchronization of human consciousness with the electromagnetic heartbeat of the planet. The relationship between climate variability and human migration is among the most consequential and actively studied topics at the intersection of atmospheric science and human history. The Dust Bowl of the 1930s, a decade-long agricultural and ecological catastrophe in the American Great Plains produced by the combination of prolonged drought, poor land management, and extreme dust storm events, displaced an estimated 3.5 million people, producing one of the largest internal migrations in American history. The migrants immortalized in John Steinbeck's The Grapes of Wrath were, at their root, climate refugees. The Norse settlement and subsequent abandonment of Greenland's western settlement in the 14th century correlates with the onset of the Little Ice Age, a period of lowered northern hemisphere temperatures associated with reduced volcanic activity and changes in solar output. The Bronze Age collapse of approximately 1200 BCE, which saw the simultaneous disappearance of multiple Eastern Mediterranean civilizations within a generation, is now strongly suspected by archaeologists to have been triggered or significantly exacerbated by a prolonged regional drought, a climate event that severed the agricultural foundation of several interconnected palace economies simultaneously. Storm and drought are not peripheral to human history, they are woven into its fundamental structure. Few natural phenomena are as familiar as rain, and yet the physics of raindrops rewards close examination with a series of surprises. The conventional depiction of a raindrop, a teardrop shape, pointed at the top and rounded at the bottom, is in fact physically incorrect. A falling raindrop assumes a shape determined by the balance between surface tension, which acts to minimize the drop's surface area and produce a sphere, and aerodynamic pressure, which deforms the sphere as it falls through the air. For very small drops below approximately 1 millimeter in diameter, surface tension dominates and the drop is essentially spherical. As size increases, aerodynamic pressure flattens the drop's base, producing the shape more accurately described as a hamburger bun or oblate spheroid. At diameters above approximately 4 to 5 millimeters, the drop becomes unstable. The upward aerodynamic pressure creates a concavity in its base that deepens until the drop breaks up into smaller droplets. Maximum stable raindrop size is therefore self-limiting. The terminal velocity of a raindrop varies with its size, ranging from approximately 2 meters per second for a small drizzle drop to approximately 9 meters per second for the largest stable drops. This velocity differential means that larger drops collect smaller ones as they fall, a process called coalescence that is one of the fundamental mechanisms of precipitation growth. In arid and semi-arid regions of the world, the American West, the Middle East, the Australian interior, one of the most visually striking atmospheric phenomena is virga, precipitation that falls from a cloud base but evaporates completely before reaching the ground. Observed from a distance, virga appears as diaphanous gray-blue streaks or curtains hanging beneath a cloud, often curved by the wind into elegant trailing wisps that taper to nothing before the ground. The precipitation forming virga is genuine rain or snow that has fallen from a cloud into a layer of extremely dry air below. As each raindrop or snowflake falls into this drier layer, it begins to evaporate, cooling the surrounding air as it does so, since evaporation is an endothermic process that absorbs latent heat from the environment. This evaporative cooling can generate a mass of air significantly denser than its surroundings, which descends rapidly as a microburst, a localized, extremely intense downdraft that poses a severe hazard to aircraft during approach and departure, when the airspeed changes required to navigate the sudden shift from headwind to tailwind may exceed the aircraft's performance margins. Virga-generated microbursts have been implicated in several catastrophic commercial aircraft accidents, most notoriously the crashes of Delta Airlines Flight 191 at Dallas-Fort Worth in 1985 and Eastern Airlines Flight 66 at JFK in 1975. The instrumental record of weather extends back only a few centuries at most, a blink of geological time in the context of Earth's 4.5 billion year history. Yet traces of past storms are preserved in a remarkable variety of geological and biological archives that paleoclimatologists have learned to read with increasing sophistication. Overwash deposits, layers of marine sediment carried inland by hurricane storm surges, preserve in coastal stratigraphy a record of major hurricane landfalls extending back thousands of years. Analysis of these deposits in the Gulf of Mexico and Atlantic coast of the United States has revealed that the period of frequent intense hurricanes we have experienced since approximately 1995 is not unusual in the longer context of Holocene climate, and that periods of hyperactive hurricane activity lasting centuries occurred multiple times during the past 5,000 years. Similarly, speleothems, cave formations like stalagmites and stalactites, preserve oxygen isotope ratios that record past precipitation patterns with annual resolution in some cases. Tree rings document drought and flood sequences in their growth patterns. Ice cores from Greenland and Antarctica carry chemical signatures of volcanic eruptions, wildfires, and even specific dust storms from millennia past. The storm has left its fingerprints everywhere, for those with the tools to read them. Snow is not merely frozen rain. The crystalline structures that constitute a snowflake, among the most visually intricate objects produced by any natural process, form through an entirely different pathway than the coalescence processes that produce liquid precipitation. A snowflake begins as a water molecule that freezes onto an ice nucleus in the upper portions of a cloud, forming a tiny hexagonal ice crystal. The hexagonal symmetry is not arbitrary. It reflects the molecular geometry of water molecules, which form hydrogen bonds in a six-fold symmetric arrangement as they transition from liquid to solid. As the growing crystal falls through the cloud, it encounters slightly varying conditions of temperature and humidity, and at each condition, ice grows preferentially on different surfaces of the hexagonal structure, producing the characteristic dendritic, or branching, patterns. The remarkable claim that no two snowflakes are alike is not quite a mathematical certainty but is effectively true for the complex dendritic forms produced under most natural conditions, since the exact sequence of atmospheric conditions encountered by each crystal as it falls is unique. Simpler forms, hexagonal plates, columns, needles, are more likely to be repeated. Snow physicist Ukichiro Nakaya's 1950s laboratory study of ice crystal morphology produced the first comprehensive chart of crystal forms as a function of temperature and supersaturation, one of the most beautiful scientific diagrams in the meteorological literature. The atmosphere is not simply a mixture of gases, it is a suspension of billions of microscopic particles whose influence on cloud and storm development is profound and, in many respects, still being quantified. Aerosols, airborne particles ranging from natural sea salt and mineral dust to anthropogenic pollutants including soot, sulfate, and various organic compounds, serve as the condensation nuclei upon which cloud droplets form. The number and nature of available aerosols profoundly influence cloud properties. Clouds forming in aerosol-rich environments tend to contain more numerous but smaller droplets than clouds forming in clean air. This difference has several important consequences. More numerous smaller droplets reflect sunlight more efficiently, the first aerosol indirect effect, which tends to cool the climate. Smaller droplets are also slower to coalesce into precipitation-sized drops, the second aerosol indirect effect, potentially suppressing precipitation and prolonging cloud lifetime. In heavily polluted environments, these effects may suppress warm rain processes entirely, forcing moisture to be carried to higher altitudes where it freezes and contributes to electrification. Research has suggested that downwind of major urban areas and industrial regions, thunderstorms may be more intense and lightning more frequent than in comparable regions with cleaner air, the city itself, in some sense, generating the conditions for a more electric sky. In the summer of 1588, Philip II of Spain dispatched a fleet of 130 ships and approximately 30,000 men northward from Lisbon with orders to rendezvous with the Duke of Parma's army in the Spanish Netherlands, escort it across the English Channel, and overthrow Elizabeth I of England. The English fleet, under Admiral Howard and Francis Drake, intercepted the Armada in the Channel and, through a combination of naval tactics and the use of fireships at Gravelines, disrupted the Armada's formation and forced it northward around the British Isles. But it was the weather, not the English Navy, that ultimately destroyed the Armada. A powerful North Atlantic storm system swept the fleet as it attempted to round Scotland and Ireland, driving many ships onto the rocky western coasts of Ireland and Scotland where they were wrecked. Modern meteorological reconstructions of the 1588 storm pattern suggest an unusually deep and persistent Atlantic cyclone, possibly linked to an El Niño event that year, produced conditions far more severe than the late summer season would normally generate in northern waters. Approximately 24 ships were wrecked. Perhaps 5,000 men perished in the storms alone. The storm did not merely affect history, it arguably determined it, preserving the Protestant succession in England and altering the trajectory of European geopolitics for the following century. Above active thunderstorms, at altitudes ranging from 40 to approximately 90 kilometers, a menagerie of transient luminous events, given evocative names by the scientists who first documented them, occurs with far greater frequency than was suspected before sensitive photographic technology made their detection possible. Sprites are large-scale electrical discharges occurring in the mesosphere, typically red or orange in color, that appear above intense positive cloud-to-ground lightning strokes. They can extend from approximately 40 to 90 kilometers altitude and persist for only a few milliseconds, but their spatial extent can reach 100 kilometers. ELVs, an acronym for emissions of light and very low-frequency perturbations from electromagnetic pulse sources, are expanding rings of luminescence that occur at approximately 90 kilometers altitude in the ionosphere as the electromagnetic pulse from a lightning stroke propagates upward. Blue jets are narrow channels of blue or violet light that erupt from cloud tops upward to altitudes of approximately 50 kilometers, apparently driven by lightning or lightning-associated electrical activity within or just above the thundercloud. These phenomena were largely unknown to science before the 1990s, not because they are rare, but because ground-based observation required exactly the right combination of darkness, clear skies, and a camera pointed at the sky above a distant storm. They are now actively studied as key elements of the global electric circuit. The Earth possesses a permanent, planet-scale electrical circuit that links the surface, the atmosphere, and the ionosphere in a continuous flow of electric current. The circuit is maintained by the collective action of the approximately 2,000 thunderstorms active on Earth at any given moment, which collectively act as an enormous battery, charging the ionosphere to an average potential of approximately 250,000 volts positive relative to the Earth's surface. In fair-weather regions away from active thunderstorms, this potential drives a gentle, downward return current through the atmosphere at a density of approximately 2 picoamperes per square meter, so faint as to be imperceptible, yet globally significant in its aggregate. Without the continuous charging provided by thunderstorms, atmospheric electrical leakage would dissipate the global charge separation within approximately 10 minutes. The global electric circuit was first inferred from observations made during the circumnavigation voyages of the Carnegie research vessel in the early 20th century, which documented a consistent daily variation in the fair-weather electric field, the Carnegie curve, that correlated with the known global distribution of thunderstorm activity peaking in the late afternoon hours of universal time over Africa, America, and Asia in succession. The thunderstorm, in this view, is not merely a local event. It is a charging station for the planet. In late October of 1991, an unusual convergence of 3 meteorological systems produced one of the most powerful extratropical cyclones ever observed in the North Atlantic, a storm that became known both through Sebastian Junger's 1997 book and its subsequent film adaptation as The Perfect Storm. The event began with a large high-pressure system over Canada meeting a classic nor'easter off the New England coast. At the same time, the remnants of Hurricane Grace, itself a major hurricane weakening as it moved northward into cooler waters, were absorbed by the intensifying nor'easter, injecting tropical moisture and additional energy into the system. The resulting cyclone produced significant wave heights in excess of 30 meters in the open North Atlantic, with wave heights of 9 to 15 meters measured along portions of the New England coast. The storm caused widespread damage across the eastern seaboard and claimed the lives of 12 people, including the 6-man crew of the Andrea Gale, a swordfishing vessel that was caught in the storm's peak intensity several hundred kilometers east of Nova Scotia. The meteorological rarity of the event resided in the precise timing of the 3 components' interaction, a confluence of systems that the atmospheric record suggests occurs perhaps once in a generation. Between approximately 700 and 635 million years ago, geologic evidence suggests that the Earth may have experienced one or more episodes of near-complete global glaciation, events so extreme that sea ice extended to the equator and average global temperatures fell to approximately minus 50 degrees Celsius. This snowball Earth hypothesis, developed primarily by geologist Joseph Kirschvink and subsequently elaborated by Paul Hoffman and Daniel Schrag, is supported by evidence from glacial deposits found at tropical latitudes and unusual isotopic signatures in carbonates from the relevant geological period. Under snowball Earth conditions, the storm systems and atmospheric circulation patterns that characterize today's climate would have been radically different, driven by whatever residual temperature gradients existed between the ice surface and the polar regions, likely generating a more sluggish circulation than the modern atmosphere. The escape from snowball Earth is thought to have occurred through the accumulation of volcanic carbon dioxide, which continued to be released through the ice regardless of surface conditions, eventually raising greenhouse forcing to a level sufficient to trigger a catastrophic and rapid deglaciation. The storms that followed the snowball Earth's melting, with vast quantities of water evaporating rapidly from a suddenly warm surface, may have been among the most intense in the planet's atmospheric history. Between the scale of the individual thunderstorm cell and the scale of the large synoptic cyclone, atmospheric science recognizes a category of organized convective systems called mesoscale convective systems, coherent ensembles of thunderstorms that organize on spatial scales of hundreds of kilometers and temporal scales of hours, often developing internal circulations and dynamics that sustain them long past the lifetime of their constituent individual cells. Mesoscale convective systems include squall lines, bow echoes, and mesoscale convective complexes, a subtype defined by specific satellite signatures of cold cloud top temperature and organizational geometry first characterized by meteorologist Robert Maddox in 1980. Mesoscale convective complexes are among the most important precipitation producers in the central United States, responsible for a substantial fraction of growing season rainfall across the Corn Belt, and they form preferentially at night, a characteristic linked to a nocturnal low-level jet that develops over the Great Plains after sunset and provides both moisture transport and wind shear at low levels. The nocturnal nature of these systems means that they were historically among the most poorly observed features of the atmospheric circulation, since the operational radiosonde network observed the atmosphere at fixed times that often missed the system's development. Their full contribution to the regional water balance was not appreciated until the advent of continuous satellite coverage. No meteorological phenomenon has generated a richer cultural and mythological response across human civilizations than the tropical cyclone. Encountered under different names by different peoples in different ocean basins, but everywhere experienced as an event of sufficient violence and consequence to demand religious, narrative, and artistic explanation. The word hurricane derives from the Taino word jurican, a deity associated with chaos and destruction in the cosmology of the indigenous Arawakan peoples of the Caribbean, who had lived with these storms for millennia before the arrival of European explorers. In Japan, the kamikaze, the divine winds that destroyed two Mongol invasion fleets in 1274 and 1281, were in all probability powerful typhoons or their remnants, and their perceived divine intervention shaped Japanese self-understanding for centuries. The Mayan deity Huracan was one of the principal creator gods in the Popol Vuh. In Hindu tradition, the storm deity Vayu represented both the destructive power of wind and its life-giving quality as the breath of the universe. In most of these traditions, the storm is not simply a natural hazard. It is a communication, a demonstration of a power that dwarfs human agency, and an invitation to consider the fragility of the built world in the face of atmospheric physics operating at its most unrestrained. Since the 1940s, when General Electric scientist Vincent Schaefer discovered that dry ice pellets dropped into a supercooled cloud produced a cascade of ice crystal formation, scientists and governments have pursued the possibility of deliberately modifying weather through a process called cloud seeding, the introduction of particles into clouds that serve as additional ice nuclei, intended to promote precipitation formation or, in some applications, to reduce hail size or suppress fog. The most widely used seeding material has been silver iodide, whose crystal structure closely mimics that of ice and allows it to serve as an efficient ice nucleus at temperatures only a few degrees below freezing. China operates the world's largest weather modification program, with thousands of cloud seeding operations conducted annually using both ground-based generators and aircraft, targeting drought mitigation, hail suppression, and fog dispersal. The scientific evidence for the efficacy of cloud seeding is substantially better than it was in the early decades of the field. A 2020 study of seeding operations in Idaho using airborne measurements provided compelling evidence of precipitation enhancement. Nevertheless, the practical returns, a modest percentage increase in precipitation from seeded clouds under appropriate conditions, remain modest relative to the scale of the global water cycle and the fundamental difficulty of proving causality in an atmosphere where precipitation might have occurred anyway ensures that controversy remains part of the field. The atmospheric phenomena discussed in most meteorological discourse occur at scales ranging from the local to the planetary, but some of the most practically consequential weather occurs at the subkilometer, neighborhood, and street level, in the microclimates generated by topography, vegetation, water bodies, and human infrastructure. Urban heat islands, regions within cities where the concentration of heat-absorbing surfaces, waste heat from buildings and vehicles, and reduced evapotranspiration relative to surrounding vegetated areas creates temperatures several degrees Celsius warmer than the surrounding countryside, influence the development and intensity of convective storms. Some studies have documented a downwind precipitation shadow, where cities reduce rainfall, while others have found enhanced convective triggering over urban centers. Valley floors and coastal plains develop their own characteristic fog, wind, and temperature regimes that differ substantially from surrounding areas. Sea breezes and lake breezes, local circulation systems driven by the differential heating of water and land surfaces, can trigger afternoon thunderstorms along coastlines with a regularity that experienced local meteorologists can predict with confidence. The microclimate is the storm at a human scale, the world that each individual inhabits, shaped not by global circulation patterns but by the specific geometry of the land, water, and city that surrounds them. The spin of a hurricane, counterclockwise in the northern hemisphere, clockwise in the southern, is not an arbitrary choice of nature but a necessary consequence of one of the most important forces in geophysical fluid dynamics, the Coriolis effect, named for the French mathematician Gaspard Gustave de Coriolis, who derived its mathematical expression in 1835. The Coriolis effect is not a true force in the classical mechanical sense but an apparent deflection experienced by objects moving across the surface of a rotating body. On Earth, the surface rotates at different velocities depending on latitude, fastest at the equator and zero at the poles, and this gradient of velocity causes freely moving air to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. As air rushes toward the low pressure at the center of a developing cyclone, the Coriolis deflection causes the inflow to curve, imparting an anti-clockwise rotation in the northern hemisphere and a clockwise rotation in the southern. The Coriolis effect is vanishingly small at very small scales. The popular claim that it determines the direction of water draining from a bathtub is, while technically true in principle, completely overwhelmed in practice by the far larger initial conditions of the bathwater's motion. But at the scale of a hurricane or a mid-latitude cyclone, it is the fundamental organizing force of the storm's rotation. Among the most important and best documented relationships in global climate science is the teleconnection between the El Niño southern oscillation cycle in the tropical Pacific and the behavior of the Indian summer monsoon, a relationship that links the rainfall received by more than 1 billion people in South Asia to sea surface temperature anomalies in an ocean basin thousands of kilometers away. The linkage operates through changes in the Walker circulation, the large-scale zonal overturning circulation in the tropical atmosphere driven by the contrast in sea surface temperatures between the warm western Pacific and the cooler eastern Pacific. During El Niño, the anomalously warm eastern Pacific draws convective activity eastward, weakening the rising branch of the Walker circulation over the Indian Ocean and maritime continent. This weakening reduces the moisture convergence and convective uplift over South Asia that fuels monsoon rainfall, increasing the probability of deficient monsoon seasons and drought across large parts of India and Southeast Asia. The 1877 to 1878 and 1899 to 1900 El Niño events were associated with catastrophic monsoon failures that contributed to famines killing tens of millions of people across India, China, and Brazil. Understanding and improving the prediction of ENSO monsoon teleconnections has therefore been among the highest priority objectives in applied climate science for decades. The storm produces sound across a range of frequencies that extends far below the threshold of human hearing, into the infrasound domain, generally defined as sound below 20 Hz. These low-frequency acoustic waves, generated by lightning, by pressure oscillations in convective systems, by the roar of the ocean surface under hurricane-force winds, and by the interaction of turbulent atmospheric flow with the land surface, propagate through the atmosphere with extremely low attenuation, meaning they travel great distances with comparatively little energy loss. Infrasound detectors, originally deployed as part of the global network designed to monitor nuclear test ban treaty compliance by detecting the infrasonic signatures of nuclear explosions, routinely record infrasound from storms at distances of thousands of kilometers. Some species of animals appear to perceive and respond to infrasound, Elephants are known to communicate via infrasound over distances of several kilometers, and there is behavioral evidence that some animals detect the infrasonic precursors of approaching severe weather before any other cue is available. Certain persistent, locally experienced infrasound phenomena, the mysterious rumbling or thrumming reported by residents of specific geographic locations, have been attributed in some cases to the interaction of ocean waves and the complex topography of the seafloor, creating a global infrasonic background often called the hum, to which storms contribute significantly. The storm is not merely a hazard, it is an ecological force of enormous importance, driving processes of renewal, dispersal, and nutrient distribution that are integral to the function of multiple ecosystems. Tropical cyclones passing over the ocean drive intense upwelling that brings cold, nutrient-rich deep water to the surface, fertilizing the photic zone and producing blooms of phytoplankton visible from satellite imagery as enhanced chlorophyll concentrations in the storm's wake. These blooms propagate up the food chain, producing elevated productivity in the ocean ecosystem for weeks after a storm's passage. On land, the wind throw of trees during severe storms creates canopy gaps that are critical for the regeneration of shade-intolerant species. Without periodic disturbance, many forest ecosystems would transition to a climax state dominated by a smaller number of shade-tolerant species, reducing biodiversity. In fire-dependent ecosystems, lightning is the primary natural ignition source, the spark that maintains the savanna, that clears the accumulating deadwood of the boreal forest, that allows the serotinous pine species whose cones open only under intense heat to regenerate after decades of competitive suppression. The longleaf pine ecosystem of the southeastern United States, one of North America's most biodiverse and most endangered, evolved in a landscape defined by frequent lightning-ignited fires. Remove the lightning, and the ecosystem transforms beyond recognition. The lightning stroke most familiar from human experience, the brilliant flash connecting cloud base to Earth's surface, is, somewhat counterintuitively, not the most common type of lightning discharge. Intracloud lightning, which occurs entirely within or between cloud systems without reaching the ground, accounts for approximately 75% of all lightning discharges globally. Cloud-to-ground lightning, while less frequent, carries greater consequences for human life and infrastructure and has therefore received disproportionate research attention. Within cloud-to-ground lightning, several distinct varieties have been documented. Negative cloud-to-ground strokes, in which negative charge is transported from the cloud to the ground via the mechanism of the stepped leader and return stroke described earlier, are by far the most common. Positive cloud-to-ground strokes, which transport positive charge from the upper regions of the cloud to the ground, are far less frequent, approximately 5 to 10% of all cloud-to-ground strokes, but tend to be considerably more powerful and more dangerous per strike. Positive strokes can occur at distances far greater from the cloud's visible precipitation core than negative strokes, giving rise to the concept of the bolt from the blue, a positive stroke occurring from a clear sky, sometimes kilometers from the nearest cloud, with no preceding local thunderclap to provide warning. They are responsible for a disproportionate fraction of lightning fatalities and large wildfires. Within the architecture of a mature thunderstorm, two opposing vertical air currents coexist in a dynamic tension that determines the storm's character, longevity, and hazard profile. The updraft is the ascending current of warm, moist air that feeds the storm from below, the engine of convection, transporting latent heat energy aloft where it is released through condensation and fueling the explosive vertical development of the cumulonimbus. In the most powerful supercell thunderstorms, updraft velocities can exceed 160 km per hour, sufficient to suspend and accumulate baseball-sized hailstones for considerable periods before their weight overcomes the lifting force. The downdraft is the descending current of cold, heavy air that develops as precipitation loading, evaporative cooling, and entrainment of dry environmental air cool and densify portions of the storm's cloud mass. The rear flank downdraft, a specific downdraft feature of supercells descending alongside the mesocyclone, plays a critical role in tornadogenesis, wrapping around the storm's southern flank and generating the rotation and convergence at the surface that can initiate and maintain a tornado. When a storm's downdraft reaches the surface, it spreads outward as a density current, the gust front. lifting surface air ahead of it and potentially triggering new convection. The balance and interaction between updraft and downdraft is the storm's internal conversation with itself. For all the sophistication of satellite remote sensing, Doppler radar networks, and numerical weather prediction models, the foundation of operational meteorological observation remains a remarkably humble instrument, the radiosonde, a small package of sensors attached to a hydrogen or helium balloon that ascends through the atmosphere measuring temperature, humidity, and pressure as it rises, while its position drift tracks wind speed and direction. Twice daily, at 0000 and 1200 Coordinated Universal Time, approximately 800 upper air stations around the world simultaneously release radiosondes, creating a near-instantaneous global snapshot of the three-dimensional state of the atmosphere that is ingested into numerical weather prediction models worldwide. The radiosonde was invented in the 1920s, and while its basic principle has remained constant, the sensors, data transmission, and processing have been continuously refined. Modern radiosondes transmit their measurements by radio-to-ground receivers every second throughout their ascent to altitudes of approximately 30 kilometers, where the balloon eventually bursts and the sonde descends under a small parachute. Many are recovered and recycled. The twice-daily global sounding network is an extraordinary exercise in international scientific cooperation, a shared measurement infrastructure maintained through geopolitical changes, wars, and pandemics because the numerical models that protect lives by predicting severe weather depend on it. Among the most dangerous and scientifically remarkable meteorological phenomena documented in recent decades is the pyrocumulonimbus, a cumulonimbus cloud that develops from the extreme convective plume of a large, intense wildfire. As a sufficiently hot fire releases heat into the boundary layer, air rises rapidly and draws in surrounding air, creating a fire-induced convective column that can, under the right atmospheric conditions, develop into a fully electrified thunderstorm cloud with tops reaching the upper troposphere. Pyrocumulonimbus events represent one of the fire weather system's most dangerous feedbacks. The storm produced by the fire can generate its own lightning, igniting new fires at distances far removed from the original. The downdrafts and outflow winds from the pyrocumulonimbus can dramatically intensify and redirect the existing fire, producing erratic and unpredictable fire behavior that has caught firefighters fatally off guard. The storm's updraft can also loft burning embers, firebrands, to altitudes of several kilometers, depositing them kilometers ahead of the fire front and initiating spot fires that overwhelm containment lines. Major pyrocumulonimbus events have been documented over the devastating 2019 to 2020 Australian bushfire season, the 2021 Western North America heat dome fires, and numerous Siberian and Canadian boreal forest fires. They inject smoke, aerosols, and water vapor directly into the lower stratosphere, affecting radiation budgets at hemispheric scales. On the night of October 15 to 16, 1987, a rapidly deepening extratropical cyclone swept across southern England and northern France, producing the most destructive windstorm to affect the region in approximately 3 centuries, an event with a legacy that extends far beyond its immediate meteorological significance. Gusts exceeding 170 kilometers per hour were recorded across southern England, killing 22 people, uprooting approximately 15 million trees, blocking major roads and rail lines, and causing property damage ultimately estimated at approximately £2 billion. The storm's particular cultural resonance in Britain stems in part from a quirk of forecasting history. On the evening before the storm, television meteorologist Michael Fish memorably told viewers that a woman who had called the BBC to ask whether a hurricane was approaching could be reassured that no hurricane was coming. Fish was technically correct. The storm was not a tropical hurricane but an extratropical cyclone, but his timing was exquisitely unfortunate. The Great Storm of 1987 became a watershed event in British meteorological history, driving significant investment in numerical weather prediction capability at the Met Office and fundamentally changing the culture of risk communication in weather forecasting. The 15 million trees fell. The science of forecasting learned from them. While major winter storms receive extensive media attention and trigger elaborate emergency preparedness responses, some of the most dangerous winter weather events occur with such brevity and localized intensity that they can outpace warning systems and catch travelers entirely unprepared. The snow squall, a brief, intense band of heavy snow with sudden onset, gusty winds, and rapid visibility reduction that can transform clear highway driving conditions into near-zero visibility within seconds. Snow squalls develop along sharp cold fronts where the temperature contrast across the boundary is sufficient to generate strong surface wind convergence and brief, intense precipitation. Their defining characteristic is their transience. Most last less than 30 minutes in any given location, combined with their extreme intensity during that period. The National Weather Service in the United States introduced the snow squall warning as a distinct warning product in 2018, modeled conceptually on the tornado warning, a short-fuse warning of imminent, life-threatening weather requiring immediate action. Multi-vehicle pileups on highways during snow squall events have caused dozens of fatalities in single incidents. The combination of sudden visibility loss, ice formation on road surfaces before road treatment vehicles can respond, and high-speed traffic creating chain reaction collision sequences that overwhelm emergency response. The snow squall's danger is precisely its brevity. It arrives and departs before most people's situational awareness has fully engaged. The practical science of protecting human beings from lightning has advanced considerably beyond Franklin's pointed conductor, incorporating a sophisticated understanding of the stepped leader attachment process, the physics of ground currents, and the epidemiology of lightning fatalities. Lightning kills between 2,000 and 4,000 people annually worldwide, with significant geographic clustering in regions combining high thunderstorm frequency with outdoor agricultural work and limited access to shelter. The majority of lightning fatalities in developed countries now occur among outdoor recreational users, golfers, hikers, swimmers, campers, who underestimate the threat or are caught in rapidly developing storms. The fundamental survival advice has not changed significantly. Seek substantial shelter in a building or hard-topped metal vehicle when thunder is heard, and avoid tall isolated objects, open fields, and bodies of water. What has changed is the understanding of ground current as a lightning hazard. A strike to nearby ground can spread an electrical potential gradient across a large area, driving potentially fatal current through any person standing on the ground nearby. The recommendation to assume a crouch position with feet together is intended to minimize the potential difference between the body's two ground contact points, reducing ground current lethality. The 30-30 rule: seek shelter when the flash-to-bang interval is less than 30 seconds, and remain sheltered for 30 minutes after the last thunder, provides a practical operational framework accessible without instruments. The historical records of tropical cyclone disasters in the Bay of Bengal stretch back through centuries, documenting a region where the combination of warm sea surface temperatures, the annual monsoon circulation, and the extreme topographic amplification of storm surges by the funnel-shaped delta coast create conditions for exceptional tropical cyclone destruction. Among the earliest well-documented events is the Calcutta cyclone of October 1737, which according to historical accounts produced a storm surge estimated at approximately 13 meters that inundated the low-lying delta regions around the mouth of the Hooghly River. Contemporary accounts describe the destruction of approximately 20,000 boats and the deaths of between 300,000 and 500,000 people. Figures that, while difficult to verify with modern statistical rigor, are consistent with the known topographic vulnerability of the region and the documented storm surge heights achievable by major Bay of Bengal tropical cyclones. The Bay of Bengal remains, in the 21st century, the world's most lethal ocean basin for tropical cyclone storm surge casualties, a situation that has improved significantly in recent decades through investment in cyclone shelters, early warning systems, and emergency evacuation infrastructure, but that reflects a fundamental geographic reality. Tens of millions of people live within a few meters of sea level in a region where the atmosphere regularly generates storms of extreme intensity. The intersection of meteorology and maritime navigation has produced some of the most consequential practical science in history, driven by the simple, brutal arithmetic that a ship in a storm too severe for its captain to have anticipated often means a ship lost and sailors drowned. The systematic collection of meteorological observations from ships at sea, which, aggregated across many voyages and many decades, began to reveal the statistical structure of the ocean atmosphere system, was championed most effectively in the 19th century by the American naval officer Matthew Fontaine Maury, whose pilot charts distilled thousands of ship logs into practical guidance for optimizing sailing routes. Maury's work was complemented by Fitzroy's Storm Warning Service and by the development of international standards for meteorological observation on ships, standards that eventually became the foundation of the global marine observation network. The ocean's thermodynamic relationship with the atmosphere, the exchange of heat, moisture, and momentum at the sea surface that drives the jet stream, feeds tropical cyclones, and modulates global climate, can only be characterized through sustained, systematic observation. Modern Argo floats, automated surface drifters, and moored buoys have largely replaced the ship officer with a barometer, but the intellectual lineage is continuous, from the mariner watching the sky at midnight to the satellite measuring sea surface temperature from orbit. In the polar regions of Greenland and Antarctica, and to a lesser extent on any sufficiently steep slope covered with a cold, dense air mass, a distinctive and powerful wind develops whose mechanism is purely gravitational. The katabatic wind, from the Greek katabatikos, meaning flowing downhill, a drainage flow of cold, dense air that pools on elevated ice sheets and then flows downslope under gravity's influence, accelerating as it descends and confined by topography into channels that can produce sustained winds of extraordinary velocity. The katabatic winds of Antarctica are among the most powerful sustained surface winds on Earth. At Commonwealth Bay on the Antarctic coast, described by the explorer Douglas Mawson, who spent a nightmarish year there between 1912 and 1913, as the home of the blizzard, average annual wind speeds exceed 22 meters per second, with gusts documented well above 60 meters per second. These are not storm-driven winds in the conventional sense. They are generated entirely by the temperature differential between the cold, dense air on the Antarctic plateau and the relatively warmer air over the adjacent ocean, continuously maintained by the relentless radiative cooling of the snow surface. Katabatic winds carry enormous quantities of snow from the interior of Antarctica toward the coast, playing a significant role in the mass balance of the ice sheet. The lifetime of an ordinary air mass thunderstorm, in contrast to the supercell's extraordinary longevity, follows a characteristic three-stage progression that meteorologists have described as the ordinary cell life cycle. The cumulus stage is defined by a single, dominant updraft that lifts warm, moist surface air to great heights, building the visible cumulonimbus tower and carrying water vapor upward where it condenses and eventually freezes. During this stage, precipitation is forming within the cloud but has not yet reached the surface. The mature stage begins when precipitation is heavy enough and the downdraft sufficiently developed to reach the surface, spreading outward as the gust front. This stage is characterized by maximum storm intensity, the heaviest rainfall, most frequent lightning, strongest winds, and largest hail. The downdraft now dominates the storm's low-level inflow, effectively cutting off the supply of warm, moist air that fueled the updraft. This self-defeating character of ordinary thunderstorm dynamics is what limits their lifetime, typically between 30 and 60 minutes from initiation to dissipation. The dissipating stage is dominated by downdraft and precipitation, with the updraft collapsing and the cloud beginning to evaporate. This inherent self-limiting quality is what the supercell overcomes through its tilted updraft structure, which separates the updraft and downdraft spatially, allowing both to coexist without one suppressing the other. A tropical cyclone is, in thermodynamic terms, a heat engine, a system that converts the thermal energy of the warm tropical ocean into the kinetic energy of wind, wave, and precipitation, operating on a cycle that the physicist Carey Emanuel has quantified with elegant precision. The fuel of this engine is the flux of heat and moisture from the warm ocean surface to the overlying atmosphere, a flux that intensifies as wind speeds increase and the wave-roughened ocean provides more surface area for evaporation. The resulting intensification is a positive feedback. Higher winds drive more evaporation, which provides more energy, which drives higher winds. The upper limit to this process is set by the thermodynamic efficiency of the heat engine, determined by the temperature difference between the warm ocean at the base of the cycle and the cold upper troposphere at the top, and by the dissipation of energy through surface friction. Immanuel's maximum potential intensity theory, which calculates this theoretical upper bound, has proven remarkably accurate as a predictor of the observed intensity ceilings of real tropical cyclones. The theory also implies a direct link between sea surface temperatures and hurricane intensity potential, a link that has significant implications for understanding how hurricane activity may change as the ocean warms. The storm is fed by the ocean, and the ocean is warming. When a cumulonimbus tower reaches the tropopause, the thermal lid that separates the troposphere from the stratosphere, its upward momentum is arrested by the temperature inversion at this boundary, where temperatures, having fallen steadily through the troposphere, begin to rise with altitude in the stratosphere due to ozone absorption of solar ultraviolet radiation. Unable to penetrate this stable layer, the cloud spreads horizontally, carried by the upper-level winds into the characteristic anvil shape, the cumulonimbus incus, from the Latin for the blacksmith's anvil. The anvil is oriented downwind of the storm's updraft tower, sometimes extending hundreds of kilometers from the main convective cell. The underside of the anvil glows with reflected light during sunset and sunrise, producing some of the most vivid atmospheric spectacle available to ground observers. Embedded within the anvil are the fast-moving horizontal winds of the upper troposphere that carry the storm's moisture and ice particles downwind, gradually evaporating as they mix with the drier environmental air. The mammatus formations on the anvil's underside, described earlier, are particularly visible here. The anvil serves also as a visual indicator of a storm's history. A wide, well-developed anvil suggests a storm of considerable vertical development and intensity, while its orientation reveals the direction of the prevailing upper-level winds, a fact that experienced storm observers and aircraft dispatchers learned to read long before Doppler radar made the storm's internal structure directly visible. Along the northeastern coast of the United States and the maritime provinces of Canada, a particular type of extratropical cyclone has left such a profound mark on both the physical landscape and the cultural consciousness of the region that it has earned its own colloquial name, the nor'easter, a powerful low-pressure system that, at its most intense, combines blizzard-force winds from the northeast, heavy precipitation, and towering ocean waves to produce some of the most challenging weather. On the eastern seaboard, nor'easters form when a disturbance in the upper-level flow develops and begins to deepen rapidly along the east coast, often with a track that carries the storm center just offshore while the strongest winds and heaviest precipitation affect the coastal zone. The proximity of the warm Gulf Stream offshore and the cold continental air mass to the northwest creates an exceptionally sharp thermal gradient that the developing low can extract energy from with extraordinary efficiency. Historic nor'easters, the blizzard of 1888, the schoolhouse blizzard of 1888 on the plains, the storm of the century in 1993, the President's Day storm of 2003, have each left lasting marks on regional infrastructure and emergency management planning. The nor'easter is not merely a hazard to the region, it is part of its atmospheric identity, as definitive of the Northeast's character as the heat and humidity of its summers. When wind encounters a building, it does not simply slow down and flow around it. It undergoes a complex transformation involving flow separation, eddy formation, pressure differentials, and resonant oscillations that structural engineers must account for in every significant building design. On the windward face of a building, air stagnates and creates a high-pressure zone, the direct load that pushes the building in the wind's direction. On the leeward face, the flow separates and creates a turbulent wake of lower pressure, effectively a partial vacuum that pulls the building toward the wind. On the side faces and roof, the accelerated flow over the edges creates areas of suction that can exceed the windward face pressure in their structural significance, which is why roof failures in hurricanes often involve the roof being lifted rather than pushed inward. The total wind load on a structure scales with the square of the wind speed. Doubling the wind speed quadruples the load. This nonlinear relationship means that relatively modest increases in peak wind speed at the upper end of the intensity range produce disproportionately large increases in structural demand. It also means that the difference in wind load between a Category 3 and Category 5 hurricane is not 60%, it is more than double. The physics of wind against a building makes the upper end of every wind speed scale genuinely qualitatively different from its lower end. The history of storm photography is, in a meaningful sense, the history of the human desire to confront beauty and terror simultaneously, to stand close enough to the storm to capture its violence without being consumed by it. The earliest photographs of storm systems came from the birth of satellite technology in the 1960s, which provided the first true overview perspective on the spatial scale of tropical cyclones and mid-latitude storm systems. Images that appeared in newspapers and textbooks and fundamentally changed the public's conceptual model of the storm from a local event to a planetary-scale phenomenon. Ground-level severe storm photography developed as a discipline alongside the growth of storm chasing in the 1970s and 1980s, motivated partly by scientific documentation and partly by the aesthetic compulsion of photographers who found in the dramatic visual landscape of the plains storm an inexhaustible subject. The work of photographers like Warren Faidley, Karsten Peter, and Mike Hollingshead documented the visual complexity of supercell thunderstorms with a level of resolution and artistry that had never previously been available. Social media has democratized storm photography dramatically, making images of unusual or extreme weather phenomena globally available within minutes of their occurrence. The result has been both a proliferation of extraordinary atmospheric imagery accessible to the public and, occasionally, dangerous situations in which photographers prioritize documentation over survival. The impact of deep convective systems, thunderstorms, and their anvil shields on the Earth's radiation budget is a subject of continuing scientific investigation and some genuine complexity. Clouds affect radiation in two opposing ways. They reflect incoming shortwave solar radiation back to space, producing a cooling effect, and they absorb outgoing long-wave infrared radiation emitted by the warm surface and lower atmosphere, re-emitting it at the colder temperatures of their tops, producing a warming effect analogous to the greenhouse effect. The net radiative impact of a particular cloud system depends on the balance between these two effects, which is determined primarily by the optical thickness and altitude of the cloud. For low-level stratus and stratocumulus clouds, the shortwave cooling effect dominates, and these cloud types produce a net cooling influence on climate. For the thin, high-altitude cirrus clouds that constitute the anvil of a cumulonimbus, the long-wave warming effect may equal or slightly exceed the short-wave cooling, producing a near-neutral or weakly warming influence. This balance has important implications for the question of how the frequency, intensity, and geographic distribution of deep convection and the anvil clouds it produces may change as the climate warms. The thunderstorm is embedded not merely in the mechanical weather system but in the planetary radiation balance, and changes to its behavior feed back to the climate system in ways that are still being carefully quantified. The systematic classification of clouds, the attempt to impose taxonomic order on the ephemeral, the infinitely variable, the continuously transforming, is among the more quixotic and genuinely successful undertakings in the history of atmospheric science. The modern cloud classification system traces its origins to the work of the English pharmacist Luke Howard, who in 1803 published a classification of clouds using Latin terminology borrowed from natural history: cumulus for heaped clouds, stratus for layered clouds, cirrus for wispy, high clouds, and nimbus for rain-producing clouds, a system so elegant in its basic structure that it has survived, with elaborations, for more than 2 centuries. The International Cloud Atlas, maintained by the World Meteorological Organization, provides the definitive global standard for cloud classification, incorporating 10 genera, multiple species and varieties, and a growing list of supplementary features and accessory clouds. The 2017 edition of the Atlas introduced new classifications for previously undocumented formations, including Asperitas, a dramatically undulating, wave-like cloud formation whose recognition as an official cloud type was championed by the Cloud Appreciation Society. The recognition of a new cloud type in the 21st century is a reminder that even our own sky, observed by billions of human eyes across millennia, retains the capacity to produce something genuinely new, or at least newly described. The Atlas grows. the sky continues to improvise. In the upper-level atmospheric circulation, the flow of air does not proceed as a steady, uniform westerly stream. It meanders in broad, planetary-scale waves, the Rossby waves, whose ridges and troughs determine the surface weather patterns below. Under normal conditions, these waves propagate slowly eastward, carrying their associated warm and cold anomalies across the continent over periods of days to weeks. Occasionally, however, the wave pattern becomes amplified and stationary, locked in place by a combination of factors including ocean temperature patterns, topographic forcing, and internal atmospheric dynamics. Among the most significant of these blocking patterns is the omega block, so named because the upper-level flow pattern resembles the Greek letter omega, a high-pressure ridge flanked by low-pressure troughs on either side. Omega blocks can persist for 1 to 3 weeks, during which time the surface weather below the block's high-pressure center experiences persistent warm, dry, and often unusually sunny conditions, while the regions under the flanking troughs experience persistent precipitation and cool temperatures. During summer, the prolonged high pressure associated with an omega block can produce heat waves of sufficient duration to cause thousands of excess deaths. The 2003 European heat wave, which killed an estimated 70,000 people, was maintained and intensified by an extraordinary and persistent blocking anticyclone that dominated the European weather pattern for nearly 2 weeks. Of all the precipitation types that the atmosphere produces, freezing rain occupies perhaps the narrowest meteorological niche, requiring a specific vertical temperature profile that is common enough to make it a regular winter phenomenon in certain climates but narrow enough that small departures from its required conditions produce either ordinary rain or ordinary snow. Freezing rain requires a warm layer aloft, typically between approximately 1 and 2 kilometers above the surface, that melts frozen precipitation falling from higher levels into liquid rain, followed by a shallow but sufficiently cold surface layer that chills the raindrops below freezing without refreezing them. The result is supercooled liquid rain that freezes instantly upon contact with any surface at or below 0 degrees Celsius. The geographic distribution of freezing rain events reflects the climatology of the required temperature profile. The southeastern United States from the Appalachians to the lower Mississippi Valley experiences some of the world's highest frequencies of significant icing events, while the Great Lakes region, the St. Lawrence Valley, and the Atlantic Maritime provinces of Canada are among the most icing-prone areas in North America. The meteorological gradient between rain, freezing rain, sleet, and snow, the precipitation type boundary zone within a winter storm, can shift by as little as 100 meters of altitude, meaning that areas a few kilometers apart may experience radically different surface impacts from the same storm system. Among winter weather phenomena, thundersnow occupies a peculiar position, electrifying in both senses, capable of producing lightning and thunder within a snowstorm, and doing so in an atmospheric environment normally associated with the gentle, silent accumulation of snowflakes rather than the drama of convective storms. Thundersnow occurs when sufficient atmospheric instability exists within a winter precipitation system, typically either when very cold air flows over a significantly warmer surface, as over the Great Lakes and other large water bodies in autumn, or when a powerful mid-latitude cyclone produces a band of intense lift along its warm frontal zone. The deep cumulonimbus towers of summer thunderstorms are not required. Thundersnow can develop in clouds extending only to 5 or 6 kilometers altitude, provided the vertical temperature profile is sufficiently unstable within that depth. The thunder produced within a thundersnow event typically sounds more muffled and shorter range than summer thunder, because the snow falling through the air absorbs and scatters sound efficiently, limiting propagation. The lightning of thundersnow is real and potentially lethal, though it is somewhat obscured within the storm's visual opaqueness. Intense thundersnow bands can produce snowfall rates of 5 to 10 centimeters per hour for brief periods, rates that can overwhelm snow removal infrastructure and reduce visibility to near zero within a band only a few tens of kilometers wide, while areas just outside the band receive modest snowfall. The storm has served as one of the most persistent and polyvalent symbols in the human artistic imagination, a visual and narrative element that simultaneously represents external nature and internal psychological states, a canvas upon which cultures have projected their deepest anxieties, aspirations, and theological convictions across millennia. In ancient literature, the storm is invariably divine. The thunderbolts of Zeus, the raging sea of Poseidon, the cosmic tempest in the Babylonian Enuma Elish, the whirlwind from which God addresses Job in the Hebrew Scriptures. The storm as a figure of divine communication, incomprehensible power speaking to diminished human comprehension, is among the oldest and most widely distributed religious tropes in world literature. In Shakespeare, the storm is the outward manifestation of inward disorder, the tempest that opens the tempest, the storm on the heath in King Lear, the supernatural meteorological events that accompany the political violence of Macbeth and Julius Caesar. In the Romantic tradition, the storm became an expression of the sublime, the category of experience defined by Edmund Burke and Immanuel Kant as producing a mixture of terror and exaltation, a confrontation with power that dwarfs the human scale and paradoxically affirms the human capacity to recognize and respond to that dwarfing. Turner painted storms. Beethoven scored them. The storm was, and remains, one of art's most faithful subjects because it is one of reality's most faithful mirrors. The relationship between anthropogenic climate change and the behavior of storms is among the most actively researched and publicly discussed topics in contemporary atmospheric science, and among the most carefully nuanced, because the answer differs significantly depending on which type of storm is under consideration. For tropical cyclones, the scientific consensus is relatively clear on some aspects. Warming sea surface temperatures increase the thermodynamic potential intensity of tropical cyclones, suggesting that the most intense storms are likely to become more intense as the climate warms. The proportion of tropical cyclones reaching Category 4 and 5 intensity appears to have increased in observational records, though attribution is complicated by historical observing technology improvements. Storm surge heights from tropical cyclones will be elevated by the rising sea level that accompanies warming. For mid-latitude cyclones, the picture is more complex. The theory suggests that the pole-to-equator temperature gradient that drives mid-latitude storm development may weaken as the Arctic warms faster than the tropics, potentially reducing the overall frequency of mid-latitude cyclones while simultaneously increasing their moisture content and therefore their precipitation intensity. The topic is politically charged in ways that have occasionally generated more heat than light, but the scientific literature is extensive, rigorous, and increasingly convergent on several key conclusions that should inform policy discussions about infrastructure, insurance, and emergency preparedness. To understand the full scope of the storm's existence, it is worth extending our view not merely backward through planetary history but forward, toward the ultimate fate of Earth's atmosphere under the steady brightening of our aging sun. Over approximately 1 billion years, the sun's luminosity will increase by approximately 10%, sufficient, according to current models, to trigger a runaway greenhouse feedback that will eventually cause Earth's oceans to evaporate entirely. As the oceans evaporate, the storms that depend on oceanic moisture, the hurricanes, the tropical convective systems, the atmospheric rivers, will transform beyond recognition. The hydrological cycle will accelerate initially, then collapse as surface liquid water disappears. The cumulonimbus towers that have been building and dissipating for 3.5 billion years of Earth's atmospheric history will cease to exist. In the interim, across the next several million years, the character of Earth's storms will be gradually transformed by the combination of a slowly brightening sun, the long-term drift of tectonic plates that will rearrange the geography of continents and ocean basins, and whatever alterations human civilization imposes on the atmospheric composition. The storm is not eternal. Nothing is. But on any human timescale, on any civilizational timescale, it is as close to permanent as anything the universe puts on display. The symphony has been playing for 4.5 billion years. We are the newest audience. And we have arrived, mercifully, in time to hear it.